Hello, everybody. Hello, everybody.
Hello.
Hey, Al.
As described in the editorial, we're going to show how to use the Mercury program to simulate cellulose diffraction patterns with the idea of evaluating the two most commonly used ways to determine the crystallinity of a cellulose sample. These are the Segal peak height method and the peak deconvolution method. So I'm showing on the screen here now just the title slide and a photograph I took of some brown colored cotton that was growing in Lafayette, Louisiana. We went to their field day a couple weekends ago. So get on with the program here. So what this slide shows is that different programs, I'm talking about the MAUD program, the Mercury program, and the Platon program, all of which are free software. If you ask them to calculate the diffraction pattern for cellulose, they can all give you almost exactly the identical patterns. And so this is something that is a known capability, something that software engineers know how to do. There's a little discrepancy here. Gosh, I could maybe use the pointer here. No. So there's a little discrepancy here in where the peaks fall, and that's because Mercury requires a change in the default wavelength because your diffractometer has a mixture of K alpha 1 and K alpha 2 radiation, and those are averaged by the MAUD and Platon programs, and the default in Mercury is just the K alpha 1 wavelength. So sometimes you'll see this value here for the wavelength in a paper, and sometimes it's 1.5406, which is just the K alpha 1 radiation. Anyway, people know how to calculate powder diffraction. There's a widespread agreement on that. Now, this is a fiber diffraction pattern, and this is a model crystal here. It's actually a modeled pattern from work that I did with Yoshi Nishiyama a few years ago. And basically, a fiber diffraction pattern is equivalent to a single crystal rotation pattern. So here's a crystal of cellulose, and here's its axis of rotation. And we're just going to turn this around while the X-ray beam is shining on it. And all of these different spots here will be produced. And this is a model crystal. This is essentially a calculated pattern cellulose. And you see that there are lots of reflections in this modeled pattern. So if we look at this is some actual experimental data from, the slide is from a lecture by Paul Langen at the ACS meeting back in 2002. And the work's been published in the Journal of the American Chemical Society, where they took synchrotron X-ray pictures of tunicate cellulose. And you see, just like that calculated pattern I showed, there are lots of reflections. They were able to get intensities for 300 unique reflections from this pattern, this X-ray pattern. The neutron diffraction pattern is similar. It's not quite as crisp and sharp as the X-ray pattern is. But the point is that there are lots of little reflections here that don't show up when you do a powder pattern. So why are we going to use the Mercury program that allows you to calculate the powder diffraction pattern? Well, it will display molecules in different styles and orientations. It can read a bunch of different formats, including the MOL2 format file and the PDB file that you get from the protein data bank. If you just have a list of the atom name and the X, Y, and Z coordinates, that's an XYZ file, and it'll read those. It can relate the molecules to the unit cell and other molecules in a crystal. And I'll show you this, depict the hydrogen bonding or other close contacts, show the planes in the crystal, can measure all kinds of distances and angles with the molecular structure. And it's easy for me to understand and use. So I hope that you can have the same experience with it. So how do you get the Mercury and input files for Mercury? Well, you can download the Mercury program for free. after you set up a free account at the Cambridge Crystallographic Data Center, and the input file, I've published an input file that's got all of the different crystal structures of the different cellulose forms that Nishiyama had worked on. And you can read this article here in Cellulose and get its supplementary material. Or you can just send an email to me at this address. You could also go to the Journal of the American Chemical Society to get the 1-alpha and 1-beta crystal structures. You can go to the crystallography open database and get the crystal structures from them. If you get a crystal information file, that's the input file from the CCDC, or those saved for Mercury for polymers, you shouldn't use them in other programs because the extra atoms are added and the disordered atoms are deleted. So you could avoid seeing the extra atoms by checking asymmetric unit, but you can't get the deleted atoms back if you use the crystal information files from the CCDC. Okay, so what is a crystal information file? The Cellulose 3 file that I have is a very simple one, and I created it myself. I found another crystal information file for methyl cellobioside, which has the same P21 space group. And I put the coordinates in the unit cell dimensions for the structure you want. You put them in place of the originals. And then you can visualize the CIF, or crystal information file, with any text editor. Windows use Notepad. Mac OS uses TextEdit. Linux, well, you can't use Linux without using a text editor, so you know what I'm talking about. But if you modify the file with a word processor, which I don't recommend, you can save it as a TXT file and then change the extension to CIF, and you should be able to still read it. So here's the guts of a crystal information file. You see the leftover from the methyl cellobioside here. All that, I just borrowed it. And here's the symmetry that you're going to use here with the twofold screw axis symmetry. So here's one of the atoms, and then here's the symmetry related atom, which has these coordinates. And here we have the unit cell A, B, C dimension, the alpha and beta monoclinic angle, gamma here. The other two are 90 by definition. Then here's a list of the coordinates, and this loop says, well, first we have the label and then the symbol, and then the fractional X, fractional Y, and fractional Z. So here's the label, the symbol, and the X, Y, and Z fractional coordinates in the unit cell. And here's the rest of the atoms, and then an end. It couldn't be more simple. You notice there's nothing about amorphous cellulose in here, nothing about a background or anything like that. So there's three main methods of cellulose crystallinity determination, and there's a fourth one that's just coming online that I've been giving people a bad time about. That's in some Bruker software. But the original cellulose methods are the Segal method, which is the Segal peak height method from 1959. The peak deconvolution method, which is continuing to evolve. It was first proposed in the 1940s based on film data. Excuse me. There's a recent paper in Cellulose by Yao et al. The Rietveld method is the one that I am focusing my efforts on these days. And there's a really good book that was published quite a long time ago by Ray Young in Atlanta. I published a paper on Rietveld with him back in 1986, I think, but I didn't do anything at all with it until much more recently myself. So here's the Segal method revisited here. Nothing radical. No, here's a nice powder pattern for cellulose that doesn't show all those individual points, and we'll get to that when we do mercury. But the Segal equation is the crystallinity index is just the intensity of this tallest peak minus the intensity at what is called the intensity for the amorphous point, and divided by this tallest intensity. So here's where the amorphous intensity is measured. And this is the peak label. This is two peaks, two major peaks next to each other or adjacent, and they overlap. And so you can just calculate, say this is 10,000 counts on this for the 200 reflection, and 2,500 here. So if you subtract 2,500 from 10,000, you get 7,500, and that equates to 75% crystallinity. So the other thing that's of interest here on this slide is here's the peak width at half the maximum height. So at 5,000 counts here, you measure this distance from here to here in degrees 2 theta, and then you can put it into the Scherer equation from 1918, and that's the beta value. So and if you're just doing this yourself in Excel or something, you have to put this in radians, the beta value. If you do it with an online program or some other program, it may be that it'll take it in degrees, but the basic theory is to have it in radians. And so if you do it yourself, that's where you have to make that conversion. And then Excel, if you want to use the trigonometry functions, the trig functions, they take radians as their arguments, not degrees also. So that's another little wrinkle in using this equation. This is just a constant. It goes from something like 0.6 to 2.5 or something. Almost everybody just uses 0.9 or 1. This is the wavelength. And the wavelength could either be in angstroms or it could be in nanometers. It's just the factor of 10 different, but that will govern what the size is. And this is the size perpendicular to the peak that you measured, perpendicular to the plane that gave the peak. So this would be the size or the distance along the 200, the vector perpendicular to the 200 plane would be the size. Anyway, as the crystal gets bigger, the size gets smaller. It's a reciprocal relationship here. So a small crystal like cellulose has will have a fairly broad peak width. And that's just basic physics. Scherer figured that out more than 100 years ago. So here's the other method that we're going to shoot down today, or shoot at anyway. It's peak deconvolution. And they just say the crystallinity is the area of the crystalline peaks divided by the area of the crystalline peaks and the amorphous broad, amorphous hump. I didn't notice that little glitch in my slide here before. So in this work by Yao and Wang and Jeff Katchmark, who's in Pennsylvania, Penn State, they deconvoluted this experimental pattern here. The original data and the fitted data are completely overlapped here in this line with this crystalline peak here for the 1 - 1 0 reflection, this one for the 1 1 0 reflection, this one here for the 1 0 2 and the 0 2 1 reflections, and the big 2 0 0 reflection. And then they've added in an amorphous curve here that one of the main points of this particular paper was that they came up with a Fourier series that they could use to describe this amorphous. And I've forgotten what program they used that they could use that as well as the pseudo-Voigt curves to represent these other peaks in the diffraction pattern. Here you see that they've made a 2-point background correction. So they assumed that the intensity was actually 0 at this point and at this point. And so when they fitted the crystalline and amorphous peaks, they added to their value this background value here, which pushed that whole pattern up to where you summarize all these individual intensities to get this fitted line. And they got a very nice fit here in this pattern as they did with all the others. And another interesting thing in that work is that they ball milled a whole bunch of different cellulose relatives, including cellobiose and cellotriose and tetrose and so forth, and got almost exactly the same amorphous pattern for each one of them. So that was an interesting thing. And if they just take a normal cotton or pulp pattern and sample and ball mill it until it doesn't change the diffraction pattern anymore, that's what you get here with this sort of a pattern. So I think this is where we want to switch to the other software. And let's see, bring up the Mercury program. Okay, so are we seeing the Mercury screen here now, everybody? Is this showing up?
Yes.
Okay, thank you. So what I'm going to do is I'm going to read in this file that I mentioned that you can get, and that's the allcellulose.crystal information file. And over here on this side, you see the 1 alpha, 1 beta, cellulose 2, cellulose 3 from 1, cellulose 3 from 2. So those are the different crystal structures of just neat cellulose, pure cellulose that Nishiyama has worked on. And you see this is a three-dimensional modeling program. You can turn things around. You can change the display styles here to stick models, for instance. These extra white dots here are hydrogen atoms that are disordered in the crystal structure. So they found that, for instance, this hydrogen here sometimes spent a little bit of the time over here. And by doing that, they got a better fit of the observed and calculated diffraction intensities on that pattern with all those different spots on it that I showed. Or that was a 1 beta pattern, but the 1 alpha pattern is very similar. So another thing here that I can just point out is that this carbon atom here is the C4 atom, this atom here. So this is actually an extra atom, as is this oxygen here. It's or in this case, they showed it as this oxygen here. It's an extra one. If I don't want to see those, I could click on this asymmetric unit over here. But the Cambridge Crystallographic Data Center puts these extra atoms in, so when they make a polymer model, they can get continuity of the molecular structure from one individual repeating unit to the next. So what can we do just real quickly with this program? Well, one of the things that we can do, well, we can show the unit cell axes, for instance. So here is the C-axis with the molecule going up along the C-axis. Up means that C1 is above C4 along here's the origin and the C-axis direction, the C-axis repeat. Here's the A-axis and the B-axis, and these conform to a right-handed rule. So you can put your thumb along the A-axis, your index finger along the B, and your middle finger along the C, and it gets pretty awkward, but you can make sure that you're conforming to the right-handed rule. Okay, so another thing that we could do with that, here's the unit cell and a molecule. We can select the packing and slicing model, and in order to show it, you have to turn packing on here over on this point here. And I'll just take a real easy example here, 3 by 3 by 3 repeats in the different directions. And then we'll move it up on the screen a little bit so you can see it better. So here's a model crystal of cellulose. We can get rid of these hydrogen atoms so you can maybe get a little better view of it. And then another thing that I can show you here, we look at this. This is C1. Here's O5, C1, C2, C3, and then O5 in the next glucose residue along this molecule here. If I right-click here and say measure distances, I can go from here to here. I hit it. There's the distance between O3 and O5. And here's the distance between O2 and O6 in this structure. So that's a very convenient thing to do. Another thing we can ask it to do. I'm going to go get rid of this packing model now and push the model back down on the screen. And I'm going to show the hydrogens again. And then I'm going to ask here to have it show the hydrogen bonds. So this shows all the different hydrogen bonds that are going on here. It's a very complex structure. All these are atoms, oxygen atoms, and neighboring molecules that are involved. And it also shows CHO hydrogen bonds. So that's a nice feature here of this software. So I go back to the packing here. I forgot to show you a couple other things here. That gets pretty messy. I'm going to turn off the packing. Turn off the hydrogens and turn off hydrogen bonds. And suppose we want to see what crystal planes look like. So one of the big plane, the big peak is due to the 110 crystal plane in cellulose 1 alpha nomenclature. And that would be a plane that intersects the A axis at 1 unit cell length and the B axis at 1 unit cell length and the C axis at infinity. So it means it runs parallel to the C, the origin to C axis line here. And so to calculate a plane, I'm clicking planes and then a new plane. And then I want to do HKL. And I'll just type in the plane 1, 1, and 0 here. And there's the 110 plane showing how it cuts. And you can do that with any of the different planes that you want to do. And you can measure distances from atoms to planes and the angles between planes, all kinds of different things that you might want to do. So also, if you want, you can delete a molecule. Let's see, I'll close that window. We want to get this molecule gone. You just delete the molecule and it'll be gone. So that's something, this is actually an especially good example because of the P1 space group for cellulose 1 alpha. If you do these packing calculations for 1 beta with P21 symmetry, anything with P21 symmetry, you'll get fragments of the molecule as well as the long chains that you want. And so to get a nice picture of the crystal, you have to do some deletion. I'll let you figure that out from that point. How do you, if we want to deal with the topic of the day here, calculate packing, slicing. Oh, sorry. I got the wrong, I want to get rid of that plane. So there's the plane we put in and say delete it and it's gone. Okay, I'm going to switch to 1 beta now. So here's the 1 beta asymmetric unit, the corner chain and the center chain, just 1 glucose residue each because of the symmetry. There's the unit cell. What I'm going to do now is I'm going to calculate the powder pattern. So this is basically the pattern that I showed you on the first slide. That's the default. Didn't do anything except read in the file and say click this powder button down here. And so here's the calculated pattern. We put the cursor on a peak, for instance. If you look over here, you can see what the peak is. So I'm going to put the cursor over here, and then in the lower right corner there, it says HKL equals 200. And I could put it over here. What's this peak here? That's the 110. This is the 1 bar 0, 1 or 1 minus 1 0 peak, and all these other little guys here. So the nomenclature that shows up here depends on the convention that was used in creating the crystal information file, and that's I've got an article in Cellulose that explains why we use this particular convention. You might also see this as the 101 and the 101 bar, or 10 minus 1, and the 002 peak and so forth. That's a different convention. It's not wrong, but most of the polymer scientists use the convention that we're using here, and it's tied to the conventions that are in the crystal structure papers that we took these structures from. Another thing I'd like to point out is this peak right here. I believe that's it. Yes. You see the label in the lower right corner for this insignificant little peak. That's the 004. And you see that it's in a cluster of peaks here. Each one of these little lines shows where there's a possible calculated peak. And the 004 is not necessarily the most important one here from just the actual peaks that are present. It has a special significance on a fiber pattern because it's the 004. That means it's perpendicular to the c-axis and shows it shows the packing along the c-axis, the shift of the chains relative to each other. But anyway, as a diffraction peak and a powder pattern, it's relatively insignificant. Now what I'm going to do here is I'm going to customize this pattern because this doesn't look anything like the patterns that you're used to seeing. And here in this customized window here, I'm going to click pattern. And I'm going to change the peak width at half height. Move this out of the way so that make this 0.2. And you see it changed it a little bit here. We noticed a difference. And we can make it 0.3. Still doesn't look too much like a cellulose diffraction pattern, although you're starting to get the idea. 0.5. Now that, if you're really lucky, if you have an algal cellulose or something like that, it might look like that. If we make it 1 degree of peak width at full width at half maximum, or peak width at half maximum, now you're starting to look like what you're used to seeing. If you had a tunicate sample, which is a very crystalline cellulose, can be anyway, it might give you a pattern that looks pretty much like this. If we go to 1.6, now we're talking like something you might see in the lab for a cotton sample. If you ground it up nicely and had a random array of the fiber fragments that you chopped up with a nice sharp cutting mill. And if I go to 3 angstroms here, this might look like your wood pulp sample. So let's go back to the 0.1 pattern here. and calculate the Segal crystallinity index for this pattern. Well, you see, here's the, this actually, there's a little peak. Segal didn't think there was a peak here, and there's certainly, and almost you could call it insignificant. And it has a height here of, what does it say here? It says 243 counts out of on a 10,000 count scale. So say it's 200, 10,000 minus 200 is 9,800. So that would be a 98% crystallinity value. If we go to say 0.5 here, now we get up to a height of, let's say, well, it's only 300 counts. So that'd be 9,700. 10,000 minus 300 would be 9,700 or 97% crystallinity. But if we start getting real here, say with our 1.6 sample, now the peaks have overlapped a great deal, and we should be at about 1,000 here. So this is 10,000 minus 1,000 is 9,000. That's equal to 90% crystallinity. And if we go to our wood pulp size pattern here, then this minimum here is at about 2,500, 2,480, it says. So that's 75% crystalline. Now, you see what I've done here. I didn't have any information on amorphous cellulose in the crystal information file that I used to start this. And all I did was I changed the peak width at half height of the reflections, and that translates into a crystallite size by the Scherer equation. So as we made the peak width wider, we got to smaller and smaller crystals, and they gave broader and broader peaks that overlapped more and more to the point where we have a very significant amount of intensity here. So when you measure the Segal, do the Segal calculation, this should give you 100% crystallinity in principle, because there is no information on amorphous in this sample. But that's what the Segal Segal would say 75% crystalline, and that's really more of a reflection on the crystallite size. Now, it's true that if there is an amorphous contribution here, that's going to raise this up even higher. And so, you could come up with some sort of a method where you found the difference between what you'd expect by calculation and what the value actually was on your experimental pattern, and say, well, that much of it was amorphous and the rest of it was a size fraction. That's really why the Segal method has severe problems from a fundamental standpoint in terms of measuring the crystallinity in terms of an amorphous fraction and a crystalline fraction. Now, you may say that if the crystal is smaller, it's not really as crystalline, but that's a little bit different question than saying you've got a perfect crystal, some perfect crystals and something that looks like spaghetti in terms of the molecular organization. So anyway, that's a little bit of a picture of that. Now, the other thing that we can take away from this is, I'm going to get that out of our view here. You see, there are all these little magenta lines where there are actually peaks, and yet there aren't any peaks showing up here, or nothing to really speak of, write home about out here. And so if you use the two peaks here, the two big peaks here, the big peak here, and maybe the two small peaks here and here, plus an amorphous curve to deconvolute this, you're leaving out all of this information here that's actually crystalline, but you may count that as amorphous material. And so that's the basic knock on the peak deconvolution system, is that unless you put in a peak at each one of these little places here, you're not accounting for all of the crystalline material, and you're making up for it by adding amorphous material to the calculation. And so that's basically just not correct. So what I want to show you, the other thing that I want to show you here with this, go back to our, well, first I'll change to the Cellulose 2 diffraction pattern. So there's a Cellulose 2 diffraction pattern, and we really need to customize that, make it a little bit smaller peak, because oftentimes you'll see pattern like this for Cellulose 2. And actually there are 3 peaks here that you don't see, and we can see that real well if we make that 0.2. There's a 3rd peak there that's not insignificant, that's lurking in there. But I'll point out that this is the 110 peak, and this is the 020. It's not the 200 peak that you might guess would be there by analogy with Cellulose 1. So this is the 1 minus 10 peak over here, and the 110 peak here, so forth. But what I really wanted to show you here is that if we make this 9 degrees peak width at half maximum, you get a very broad peak here that looks just like ball milled cellulose. And so when I need a model for the amorphous cellulose in a Rietveld analysis, which it's a peak deconvolution method, just like the standard peak deconvolution method, but all the peaks that contribute, Rietveld includes all of these peaks, and it includes them in a way that's governed by the rules of physics and crystallography. But we can put in this model for Cellulose 2 and say it has a very broad peak width at half maximum, or a very small crystallite size of, say, 12 angstroms. And that's our model for amorphous cellulose that we put in there. So anyway, if we go back to our slides here and go into conclusion, the Segal crystallinity values that you get depend on the peak width at half maximum values, and they depend on the crystallite size. And so for the small cellulose crystals that we routinely have of say 3 or 4 or 5 or 6 or 7 nanometers, you're going to get broad peaks. And the intensity at the amorphous point is the sum of the amorphous and crystallite size effects. Because of the peak overlap, 100% crystalline cellulose result cannot occur for practical samples that we're going to see because of this peak overlap. And the very low crystallinity patterns, you might want to say, what is a 10% amorphous or 20% amorphous pattern look like? Well, there's no minimum in between these 110 and the 200 peaks at 18.6. It's just another point on a sloping curve, and that's really not a specified point of the measurement for the amorphous component. The whole thing is more or less amorphous, so it's not really suited to looking at low crystallinity values, and it's not, because the maximum in the amorphous occurs at about 20 to 21 degrees in our current measures of amorphous, instead of Segal's 18-degree value. The other allomorphs have peaks right there, and so you can't measure the maximum height of the amorphous material, so forth. So it's only calibrated for Cellulose 1 cotton samples, to be more specific. Peak deconvolution methods suffer because almost nobody uses all the peaks that can be observed with fiber diffraction patterns or with simulated large crystal powder patterns. The model diffraction pattern is needed for the amorphous, and a lot of people just use a simple Gaussian curve or pseudo void if they're trying hard to be crystallographic, but we think that the peaks are not actually symmetrical patterns at all, and they look more like the ball mill Cellulose patterns or this model Cellulose 2 pattern. So anyway, that's it. I'm happy to take any questions that we have here.